Hello, hello, hello. Welcome back. It is Wednesday, the 18th of February, and today we are going to be talking about electromagnetic induction. Now, I know a lot of people have been asking for a very long time now, and by a long time, I mean like a few weeks, but time is a construct, for a Discord server, and I've finally got that sorted. So I've just posted, well, I say I've got it sorted. I haven't sorted out like the welcome and rules tab yet and the stuff that I've got to do on my end. But in terms of people being able to come in, leave recommendations, leave suggestions, things like that, all of that is updated and good to go. So that you can find in a community post that I've made. You can also, once I get around to it, I'll put it in the description of all my videos. And it's also in the channel description. If you click on the channel link and kind of look at the description, you'll find it in there. And hopefully you guys can kind of populate that and we can kind of make that something sort of fun and interactive and sort of making the most of this while we have it. So today I want to talk, last time I know we spoke about motion in electromagnetic fields. So that was more like the motor effect, Fleming's left-hand rule stuff. Today I wanted to finish off the counterpart to that, which is electromagnetic induction. So as always, I'll do my thing. I'll get my mirror board out. I'll kind of talk through the theory I think is most important. But you guys know by now, I really love it when we kind of just pivot, when you guys bounce things off the chat. And then I kind of just like riff. I find that very good fun. That's part of why I'm doing this. So definitely feel free to jump in with any suggestions you've got. I will also point out the math series has actually been going quite well as well. The live solves of the math papers. Like I had a really fun time of that last time I did it, where we were doing paper 2, and I managed to make like the silliest of all exam technique errors, not even intentionally. And I'm just like, okay, this is why we're doing this. I can make all the mistakes so that you can see the mistakes, so that you can not replicate the mistakes on your own when you're doing it. So I'm going to carry on doing that. I'm thinking that's how it's going to work. I'll use the sort of weekday evening stream to continue going through some physics theory, and I'll keep doing the live solves on the math papers because I think that's better done with demonstration, and that's much more about execution skills and exam technique and not just about like the actual core content. So without further ado, which I realize I'm saying a lot now, let me close all the unnecessary tabs that I have open and then open the mirror and whiteboard, and then we'll get into it. So electromagnetic induction. People hate this topic so damn much. So much, especially around this time of year. So much of what I do is like, oh, is it electromagnetic induction time of year? Because it's like the same thing in GCSE and A level. And so I've got my textbook ready. I'm going to go through the core essentials. If I've got some time, I'll also go through some questions. As always, feel free to drop some comments if you want me to explain anything in more detail, or if you've really got anything you want me to talk about. So let's get into it. So the main thing you've got to know when it comes to electromagnetic induction, first things first, there's kind of two ways to think about it. You need relative motion between, well, hold on, before I get drawing. So we know with the left-hand rule that it's current in a magnetic field creating motion. So you have a current in a field and that creates the force. Electromagnetic induction is the reverse of that, where you have motion or a force in a magnetic field and that generates current. So with the motor effect, you put current in, you get motion out. With the electromagnetic induction, you put motion in, you get current out. So this is all about generating voltages, generating currents. So there's two ways to do that. We talk about this motion, right? So what does this motion have to be? That's relative motion between a conductor and a magnetic field. And so there's two ways of doing that. You either have the magnetic field be stationary and the conductor move through it, or you have a stationary coil, for instance, and a changing magnetic field through the coil. In both cases, you'll get relative motion. In GCSE, you talked about conductors cutting field lines, which gives you a sense of the relative motion between the conductor and the magnetic field. And when you have that, that will generate not a current necessarily, but specifically an electromotive force, the EMF, the voltage. That is what is generated. So drawing out those two cases now, getting a little bit of visual on this. So for instance, if we have a magnetic field, how am I going to draw this? I am way too zoomed out. Way too zoomed out. No, this was no error. Me and tech are no. Never ever me and tech. Me and tech do not get on. Right. So let's say we've got how am I going to draw this? So some sort of 3D situation like that. So if we're looking at a north pole there and a south pole there, so the magnetic field lines are kind of going on this kind of angle. If I have a conductor, like a wire doing that, and I lift it up, it is going to cut through those field lines. We have relative motion between the wire and the magnetic field. And so what that's going to do is it's going to generate a voltage. Now, if that wire is a closed circuit, then the voltage, then the electromotive force will be able to drive a current round. But it's very much the voltage comes first, and if allowed, that's allowed to drive a current. So that is how, that's one way of generating a voltage. The other way of generating the voltage that you will have seen is you have a coil. How am I gonna, my artistic ability is questionable. So the other way of doing it, you've got your coil and you move a magnet towards it. So either the wire is moving in the magnetic field or the magnetic field is changing in the coil. In both cases, you're going to get an electromotive force induced. Now, Lenz's law, so qualitatively, I think this is sort of understood from what you guys did at GCSE. Now we need to get a little bit more into the specifics of the A-level and the IB course, talking about the quantitative stuff. So we know that Faraday's law tells us the size of the generated EMF is going to be the rate of change of flux linkage. So let's build up to what that means. First of all, what is flux? Well, let's start from the most basic thing you know about magnetic fields from GCSE, which is magnetic field strength. Given by the letter B, this is a measure of the strength of the magnetic field, which you can tell by looking at the magnetic field by the density of the field lines. We know if we have a magnet, if I just sort of scroll to the right a little bit, if we have a magnet, you sort of draw your magnetic field. You got your magnetic field lines. The magnetic field lines always go from north to south. So they're going in this sort of direction. We can see that over here, as you move away from the magnet, there aren't that many field lines. And so the magnetic field strength is less. Whereas close to the poles, we can see the magnetic field lines are very close together. So the magnetic field strength is higher. Closer the field lines, stronger the field. We have a comment. Was there a way to depict the direction of the current just by the direction of the magnetic field? Yes. It's not in every syllabus, but technically you can use Fleming's right-hand rule. So in this particular case, if we have this diagram up here, the right-hand rule mirrors the left-hand rule. And so the fingers mean the same thing. We have motion, we have field, we have current. So in this case, if the motion is up and the, oh God, twist it around, twist it around. So if I get my thumb pointing upwards and my first finger pointing to the right, then my third finger, my middle finger is pointing away from me, which indicates that the current would be moving in this direction. So yes, there is a way to depict the direction of the current just by the direction of the magnetic field. It's by that. Of course, you might be talking as well about solenoids, and we'll get into that when we talk about Lenz's law. Now, for Faraday's law, so we've got this magnetic field strength. We know that magnetic field strength is a measure of the density of these magnetic field lines. Now, density, you sort of a measure of the closeness. If we measure it, we have this idea of magnetic flux, which is that density times the area. Now, how I conceptualize this is I have my area of coil that is being acted on, and I think about the number of magnetic field lines that that coil captures. So I kind of think of it as being like a net, and the number of field lines captured by the cross-sectional area, that's what phi is in my head. And when the magnetic flux is changing, when the number of field lines captured by my area is changing, that is when you get an EMF induced. So for instance, let's think about, so if I have, someone says, not gonna lie, I had my Imperial mech engine interview today and it kind of broke me. Ew, interesting. I'd be really curious to see, because I've heard such mixed reviews about Imperial's interview style, where some people are like, this is the most relaxed thing I've ever seen. They just asked me why I wanted to do engineering, like basic stuff. And then some people say exactly what you said, where it's like really difficult. So I'm so open to hearing what you have to say about like what happened in this interview, because that's a bit more nebulous to me. Like I kind of get the Oxbridge interviews, but Imperial stuff can be a little bit weird. Right, so kind of getting back into the sort of capturing, so some questions on personal statement, one technical question, and one brain teaser. Interesting. It's usually never as bad as you think it's gone. So here's hoping that everything kind of ends up okay, because I like, yeah. But in the meantime, you kind of got to just leave it and realize as well that your entrance campaign is now over. So now it's time to pivot towards any A levels you've got coming up in the summer. So if we've got, for instance, a magnetic field, which does something like this, let's consider a before and after case. So I'm going to draw the same magnetic field twice. If we've got a coil in that magnetic field, we can see in this orientation, it's capturing a lot of these magnetic field lines. But if we were to rotate that 90 degrees sort of into the plane of the paper, so it's kind of just side on, kind of going down into the plane of the paper, we can see it captures no field lines anymore. So by rotating this coil, it's gone from capturing field lines to capturing no field lines, and then you can rotate it through again and capture some field lines again. So when there is changing number of magnetic field lines captured by your area, that is the thing that is going to induce an EMF. Sometimes as well, in some syllabuses, you have to kind of like resolve it, so they consider the angle. I will also add one more thing, which is this N. This is magnetic flux. So magnetic flux is this phi. And N phi is called the magnetic flux linkage, which is kind of the total number of field lines captured by the total number of turns of the coil. So each turn of the coil captures a certain number of field lines. You do that for like a number of turns, and then bam, you've got your magnetic flux linkage. When this quantity changes, when this magnetic flux linkage changes, that's when you get your EMF induced. So again, thinking about the number of field lines captured by your area changing, that is going to induce your voltage. And the magnitude of that EMF is given by this equation from Faraday's law. EMF is equal to N d phi dt, rate of change of flux linkage. So we can begin to think about what sort of things would increase the size of this EMF. So we can increase the EMF by increasing the number of turns in the coil, because that will make N go up. We can use a stronger magnet, because then you're capturing more field lines. Similarly, you can use a coil of bigger area. And similarly, you can move it faster. So if you rotate it faster, then the rate of change of flux linkage will be bigger. And that is going to increase your EMF. So for instance, there's quite a common question which says that if you are rotating, similar to this setup here, if you're rotating a coil in a magnetic field, you know you're going to get an alternating voltage, an alternating EMF. So this is if you're rotating it. And so a question might be, can you redraw this for a situation where you're rotating it faster? And in that situation, it's faster, so the time period will be less, right? The entire thing will sort of shrink on that t-axis. But because it's going faster, it will also have a bigger peak EMF. So it's important to recognize that both those things are going to happen. The peaks will go up, and it will sort of move inwards on the time axis. And all of this can be given to us from this simple equation for Faraday's law, telling us how the size of the EMF changes, or telling us how to quantify the EMF for a given situation. One thing we can also do is use Faraday's law to calculate this for different situations. So this is the general situation, but we also have some specific situations. So for instance, if we have a single conductor moving in a magnetic field, so if this is just a wire, so this is the situation that's going to be similar to this first one we discussed, when you have a wire and you just sort of slice it through the magnetic field. In that case, you've got it moving through, and as it moves through, it's going to sweep out an area, and that is going to be the area you use to multiply by B to get the magnetic flux. So if this is a length L of wire, the distance it moves in time t is V times t, and so the area it moves through is LVT. So the flux is B times A, and the EMF is the rate of change of flux linkage. So if we differentiate with respect to t, you will get BLV. You just divide by time. This is the equation for a conductor moving through a magnetic field. And this is something you might recognize from your course. Now, the second thing to consider is Lenz's law. So Lenz's law tells us that this EMF that we generate by having relative motion between a conductor and a field will act in a direction such as to oppose the change that creates it. So whatever you're doing to try and make that happen is going to resist you. If you're trying to force the wire up, it's going to resist you and kind of push the wire back down again a little bit. Is that true? It is true. It is true, and I can show you why. Let's show you these applications of Lenz's law and why they oppose the motion that creates it, right? Can you explain why the number of coils amplifies the effect, please? Yes, I can. So let's consider this situation that I just described here for a single wire. Let's imagine I was holding one wire and just sort of moving it through. This is the situation I might have. BLV. Now let's say I arbitrarily was just holding two wires in my hand and decided to do the exact same thing. Well, each wire wouldn't know that I was holding another wire. It's just like, I'm a wire, I'm moving through a field, so I'm BLV. But both of those would have the same thing. So they would both have BLV, and so the sort of total EMF induced would be 2 BLV. And same thing if I was arbitrarily holding 3 wires. Move them through, I would get 3 BLV. So for n number of wires, each bit of the wire would experience its own independent EMF. And when you move it in a coil, those are kind of all in series. So when we say EMF, we could almost think of it as being similar to a cell, right? So that's a sort of, if I move a wire, From the wire's perspective, all it knows is I've got an EMF through me. I've got an EMF through me, whether I'm a sort of wire moving through a magnetic field or if I have a cell applied to me with the same EMF. But if I have a coil, so this is sort of every time I have this wire moving, it's almost like having a cell. But if I have a coil, it wraps round, and then the next time it comes round again, oh, look, I'm the same bit of wire moving in the same direction, so I experience another EMF. It's almost like adding a cell in series. And then I wrap around again, and then I get that other push. And so every time you wrap it round one more time, it's almost like adding another one of these batteries in series. So the total EMF is just N times the individual EMFs of each individual wire. And that's why it's N d phi dt. So the d phi dt is sort of per wire, and then that happens N times in series as you wrap it round. Do let me know if that doesn't make sense. I'm quite, like, I've never really thought about it in those terms before, but it is, using that analogy of like cells in series, I think is a good way to understand it. And the fact that they're in series is because they wrap around this one after the other in series. Because I can get why you think it might be in parallel because they're kind of on top of each other, but no, because it's wrapped around like it really is in series. So hopefully that makes a bit of sense. Do let me know if it doesn't. Always happy to explain it again if there's a better way of doing that. I can kind of do that slower as well if you need to. But part of me is like, entertainment for camera, be energetic, go quick. It's different. It's just different than tutoring. Right, so let's think more about how this Lenz's law applies to these different situations. So we know that, okay, we can now work out the size of the EMF that's induced, but we can think about the direction of the EMF induced and why it has to be in that direction. So for instance, we spoke, so up here, let's think about this first wire, right? Using Fleming's right-hand rule, we were moving it up. No. Oh, it's so tricky. Right, we were moving it up. And my first finger is pointing to the right because of the magnetic field. That meant the current is acting up. But hang on a minute. Now we have a current acting in a magnetic field. What's going to happen? Left-hand rule, motor effect. So as soon as that is allowed to flow in a current, well, we have current acting up, we have magnetic field acting to the right, and what will that experience? It will experience a force acting downwards. So in other words, by the very act of me pulling it upwards, it creates a current that tries to push me back down. It resists me. I have to, and the reason why this makes complete physical sense, by the way, is because I have to put energy in. I'm the one, my motion of this conductor through the magnetic field is the thing that has to push the electrons around the circuit. That EMF is not coming from a chemical store in a cell pushing the electrons through anymore. Now it is my motion that I'm giving the conductor that is physically pushing the electrons through against a little bit of resistance. So I have to do work to push those electrons around. And work done is like force times distance. So as I'm moving through, I have to push against a resistive force in order to do the work required to push that circuit round. Otherwise, if it helped me, that would be a sort of infinite energy glitch, which would break physics entirely. I have to do work against resistance to push those electrons around, so it must be resisting me, creating a force to oppose my motion that creates the current in the first place. Now, we can also think about, this is the classic case for Lenz's law. So in this particular case, we have a changing magnetic field in this coil now. And so that is going to induce a voltage. If I have a closed circuit, that means a current will drive around the coil. But what do we know about current moving in a coil? Well, that's an electromagnet. So that's going to create its own magnetic field. and the magnetic field will be such as to oppose the change that creates it. So in this case, a north pole being pushed into the coil will force the current round such as to make that a north pole and that a south pole, to resist, to repel that magnet coming in. Similarly, if I were pulling the north pole away, the current would flow in such a way as to make that a south pole and that a north pole to now resist me moving it away. It would be trying to pull it back. So whatever I'm doing, it's opposing me. And if you want to get a sense of what that direction is, a classic way to think of it, you draw an N and you draw an S and you put arrows at the tips, and those show you, as you're looking at it, which way round the current has to flow in order to make this the electromagnet as required. So here, if I'm looking at the coil and the current is flowing anti-clockwise, that is going to create a north pole of the magnet, sending magnetic field lines up towards my face. If, as I look at the coil, the current seems to be moving in a clockwise direction, that will create a south pole of the electromagnet. And so we can see in this top case, as I look at it from the left, the current looks to be going anti-clockwise. And then as I pull the magnet away, the current now looks to be going clockwise. In other words, it has changed the direction that the current moves. So that is Lenz's law. And Lenz's law also has some very interesting applications. So, for instance, if we had let's say we have a magnet, north-south, magnetic field. If we had two rings made of metal, one that wasn't quite closed and one that was closed, as I drop them both through the field, in this first instance, we have a conductor moving through a magnetic field. That will induce a voltage, but because it's not closed, no current can flow. And because no current can flow, we no longer have that resistive force being generated, so this just falls through. The closed one, current will be allowed to flow, which will create a force by Fleming's left-hand rule, so this will be resisted. So this one will fall through faster, and this one will fall through slower. I'm sure there are plenty of other applications. If you guys have interesting questions you've seen on these topics, feel free to let me know. I'll have a go at them and kind of explain how they apply. But I think, yeah, you could always, the questions tend to have some like very interesting applications. So for instance, I saw one just today where it was combining this with the idea of resonance and damping, where they had a pendulum, but at the end of the pendulum was it was a silver ring, and silver is a conductor, so the current can flow. And then there was a magnet that it was sort of oscillating up to and then away from this magnet. And then it got us to explain why there was damping. And it's because of that Lenz's law. It's because as you move this conductor towards the magnet, there's relative motion between a conductor and a magnetic field, so an EMF is induced, and because it's closed, a current can flow. That creates an own magnetic field, which is which resists the motion towards this magnet. So in other words, there is a resistive force which creates a damping effect on the pendulum. So you can start thinking of these really interesting ways this can be applied. But the idea behind Lenz's law is whenever we have anything happening with induction, there's always some resistance you're having to push against with your motion. But I just thought this was a really interesting application, thinking about that resistance, then applying to damping of an oscillator, which is just a combination you never think you're going to see in a paper. from here, we can talk about the AC generator. So you can talk about the generator, and then you can start talking about transformers. And we've got time, so I'll get into that as well. So we've kind of alluded a little bit to the AC generator because that's this guy. So the AC generator up here is when you've got a coil which is rotating inside a stationary magnetic field. As it rotates, it is going to cut field lines. The flux linkage inside the coil is going to change. And so you are going to get an induced EMF. And we've already spoken as well about the fact that that will be sinusoidal. So maybe we can talk a bit about why. Let's think about the coil in different orientations. So as I look down on the magnet, so north-south, I'm just going to draw. So when it's in this orientation and it's rotating around, given that the field lines are going in this direction, we can see that this side of the coil moving upwards and this side of the coil moving downwards is going to cause those sides of the coil to cut field lines. In this current orientation, it captures no field lines, and as it rotates, it will be capturing field lines. So in this orientation, we are getting a maximal change in the magnetic flux linkage captured, so we are getting the maximal EMF induced. So in this particular orientation, you're going to get your maximum. So that's what's happening here. Maximal field lines being cut means maximum voltage induced. At this point here, the orientation looks a little bit different. So this is when the coil is like this. So the magnetic field lines go like this. You can see it is capturing a lot of magnetic field lines in this orientation. But this time the ends are moving along these field lines. So they are going to cut no field lines. At this exact instant, the amount of magnetic field lines captured by the coil will be the same. And so that is why at this particular instance, the magnetic flux is not changing. So we get no EMF. And then, as it continues on past that point, from this zero, it was going from zero to capturing a lot, to increasing the amount of flux, increasing the amount of field lines being captured in it. So the rate of change of flux linkage was positive, so the EMF is positive. But from this point, we can see that the number of field lines being captured by the area is going to start to go down. So the rate of flux linkage is negative. There is decreasing flux linkage in the coil, which is why the EMF turns negative. And so we can see these fundamental ideas about capturing magnetic field lines and the way that changes can tell you so much about how the EMF changes as you rotate this coil around. And similarly to how I described before, you can change the EMF by increasing the magnetic field, increasing the number of turns in the coil, or moving it faster. Now, in practice, when we are doing this for the national grid, we do it at a strict 50 hertz. That is the frequency of EMF of AC current, at least in the UK. And so that's kind of a given. We don't really change that, but you can change the number of turns or the magnetic field strength in order to make that a bit bigger. What you could also do is put a split ring commutator on it. And if you put a split ring commutator, as you remember from GCSE, a split ring commutator will change the direction of the current every half turn. So in this half turn, the EMF is positive, everything's fine. Then, once that half turn is complete, the split ring commutator connects the brushes to the opposite side, so it changes the direction, and that would generate for you a DC current. So this is without a commutator. And then with a commutator, it would be exactly the same graph, but it would be flipped around every half turn. So it would look more like this. This is when you can start getting into the current laws, which are kind of not as interesting from an it feels a little bit disjointed, but since we're here, I may as well do this sort of for completeness. What we know is that if we were to measure the average current here, or the average EMF, the average voltage, it would be 0. But we know that's not really true. Like if you get the AC out of the wall, out of the sockets in the wall, we know the voltage isn't 0. And so what you can think of is, all right, what equivalent constant DC current would I need to have the same effect as this AC current coming out of the wall? Because that would be a more meaningful comparison. And so what we do is we take the root mean square. Because the only reason this thing would average to 0 is because it's changing direction. But what if we averaged it out so we didn't care about the direction? If we square everything, that is how you get the magnitude without caring about the direction. So if you square everything and then take the average square, the mean square, that will tell you the average square size, and if you square root that, that will give you the average magnitude. So the root mean squared voltage is the equivalent constant DC voltage. Or another way you can think about that is to think about power. So P equals I squared R. So you can draw the square of that graph, what we consider now a current graph. The I squared graph would look something more like this. Where this would be, let's say I naught, the maximum current. Strictly speaking, this is I squared. So P equals I squared R, and the average of this, so the root mean squared, this average power, is a half of this maximum power. If you were to sort of integrate it, we could see that the average value will be here at I naught squared over 2, because this area could fill in this area here to create a nice rectangle. And we could do the same thing in all of these areas. That equals this. That equals this. And so we could take the whole thing and make it a flat function with a value of I naught squared over 2. So I naught squared R over 2. The R's obviously cancel, and so the RMS value is equal to the maximum value of the alternating current divided by root 2. And you can do exactly the same thing to find that the VRMS is equal to the maximum voltage over root 2. And that can sort of help you convert. So as you go through, you can work out this maximum voltage generated, and just by dividing by root 2, you can work out that equivalent DC current, DC voltage even. And the final thing we need to consider for the syllabus before I go hunting for some interesting questions is transformers. Now, as always, if anything I've said hasn't made sense, feel free to drop it in the comments or in the chat, and I'll make sure to respond to that. But now we just got to finally think about these transformers for a minute. Because the explanation for transformers is quite interesting and has a lot of like this, therefore this, therefore this, therefore this. So we have a big old iron core. We have a primary coil, and we have a secondary coil. So I'm going to draw this as a step up. Walk through this with me. So if we have our primary coil, our secondary coil, we have alternating currents in the primary coil. Because we have current moving in a coil, that creates a magnetic field around the coil. Because the current is alternating, it means the current is constantly changing, and so the magnetic field is constantly changing. The magnetic field is reversing constantly. So that creates an alternating magnetic field around the coil, which then induces an alternating magnetic field in this iron core. Because we have an alternating magnetic field in the iron core, around which the secondary coil is wrapped, that means there is an alternating magnetic field in the secondary coil. Because there is a changing magnetic field in the secondary coil, that induces an EMF. That induces a secondary voltage. And because this is a closed circuit, that induced voltage is allowed to drive current in the coil. So it induces a secondary current. So this has the number of turns NP, this has a number of turns NS, this has a primary voltage, this has a secondary voltage. What we find is that, and you're used to this from the GCSE equation, we have that NP over NS equals VP over VS. So in other words, the voltage is in proportion to the number of turns of the coil. And the reason for that, as explained before, is there is a constant now changing magnetic field in this coil, in this core. And so if this has more turns on it, that will be a bigger induced, that will be a bigger flux linkage. So the bigger rate of change of magnetic flux linkage, so a bigger EMF. And similarly, if this has fewer turns than the primary, then it is capturing less magnetic flux linkage, so the voltage is less. And if we assume 100% efficiency, then the power in primary current times primary voltage will equal secondary current times secondary voltage, from which we can rearrange and we can get the relationship between the currents as well, which is the inverse of the voltage ratio. So for N and V kind of track each other, it's both secondary over primary. It's the inverse for the current. I think some of the things that you add in an A-level or IB syllabus is talking about how to ensure, because this is a big if. This is true if 100% efficient. We can think about what steps you can take to make that 100% efficient. Because, as we saw before with Lenz's law, the direction of the induced EMF is such as to oppose the change that creates it. So it's pushing back somewhat. There should be some energy loss. And so what are these losses and how do we mitigate them? Well, one thing we do is we use an iron core that is magnetically soft, which reduces. So let's talk about sort of efficiencies. So iron core reduces what's called hysteresis loss. So hysteresis, I think that's how you spell it. Hysteresis is the technical name for the constant changing of the magnetic field, it flipping back and forth, which technically requires a little bit of energy. And because it's magnetically soft, it is easy to flip back and forth, so you get very little energy lost in doing that. What we can also have is a laminated core to reduce eddy currents. Now, a good way to think about eddy currents is what we already saw. So eddy currents, we saw, for instance, this idea of the falling ring. Where did this happen? Yeah, this idea of the falling ring, right? If current is allowed to flow, it creates a sort of back EMF. It creates a magnetic field acting in the opposite direction. It creates a voltage in the opposite direction. It pushes against the change that's creating it. So eddy currents are bad. The bigger your eddy currents, as well, they're kind of currents of flowing against resistance. Eddy currents, bad. Eddy currents lead to heat loss, losses heat, all that kind of stuff. So by using a laminated core, you prevent the ability of these eddy currents to form. Those are the biggest two, hysteresis loss and eddy currents. So those are two ways in which you can reduce the loss. Now, why would you want to use the transformers in the first place? And for that, which is really kind of the final piece of the puzzle, we have the national grid system, where when we're transporting electricity through the wires of the national grid, we know that power loss is equal to I squared R. So in other words, the power loss as heat on the wires is proportional to I squared. And in order to reduce the power loss as much as possible, so we minimize P loss by maximizing I. And how do you make current really big? Sorry, by minimize. What am I talking about? Talking absolute nonsense. By minimizing I. And how do we minimize I? Well, we do that by maximizing V. So in other words, we use a step-up transformer when we're about to send it through the wires. And then we use a step-down transformer. Hello, 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 to person in chat. So we would step it up to have high voltage, to have low current through these wires. And then we would step it down to make it safe. Because if you were to touch thousands and thousands of volts, you would die. You would be dead. There would be nothing left. So they step it back down to make it safe. And this is why we have transformers. Right, what I'm now going to do, as always, feel free to drop in the chat if you have anything. But what I'm going to do in the meantime is check the IB syllabus, see if there's anything I've missed that might be of any particular interest, or any particular applications. Maybe I'll talk about the angle, just because that's relevant. But in the meantime, I don't think I see anything here that is outside of what I said. Okay. So there's a little bit in the IB syllabus about self-induction versus mutual induction. So maybe I'll talk about that. But on the whole, yeah, everything else seems to be okay. Someone says, I probably joined after the explanation, but I sort of don't understand the idea of eddy currents, to be honest. Right. Let me get into that in a bit more detail. Will you take AQA physics papers like the way you do for math? I will if you guys really want me to. I had a go at the experimental physics, like the paper 3 style, and I just did not enjoy it as much. Like, I didn't feel like I was demonstrating anything other than sort of talking about what the physics was. Whereas I think a really good use of my live solves is to demonstrate exam technique. So that's why I quite like the math, is because you can see, even though I conceptually understand it all, oh, look, I'm still making these slip-ups in like execution, or these slip-ups in exam technique. Like, I missed a question the other day, just didn't see part of the question. And so like making those sorts of mistakes lets you learn from exam technique, I think, better than going through a physics paper where all I'm really doing is saying, read the mark scheme and pick up on the language. So I think it is less useful, but if you think it would be helpful. So for instance, I had someone recommend that I go through the multiple choice questions, because when you're doing the mark scheme, they just give you the letters, right? They don't explain the answers. So maybe I'll spend some time going through the multiple choice sections of different papers so that you have some sort of like thought process behind them. And where I get it wrong, I can then think it through and come up with a better explanation. So that's on the table. Yeah, it's the wordy questions that cause problems. What I could do is I could do it sort of, if I were doing a physics paper, maybe I wouldn't write down the wordy questions, but maybe I would kind of do it out loud and mark it there on the spot. Not doing it to time, but to explain what I see in a question, how I'm breaking it down, and how I'm using the question as a launch pad to demonstrate what I understand from the syllabus, which is all you should be doing. Also, on a physics paper, feel free to write down more than is required, because they just give you the marks as and when. So if they ask for like a 3 marker, if you write enough for a 5 marker, they'll probably find 3 marks in there. If you're ever in doubt, write more. Right, getting back into it, someone was talking about eddy currents. So, okay, let me go through those in a bit more detail. Okay, let's say I am this iron core. I am an iron core. I am a conductor. I have this primary coil wrapped around me. This primary coil is putting an alternating magnetic field through me. So now I am a conductor with a changing magnetic field in me. What is that going to do to me, the iron core? It's going to induce a voltage in me. Now, what that voltage can do, because this is a fully connected body, is this can set up little teeny tiny little currents that get driven around by that changing voltage in me. And those are called eddy currents, which kind of eddy, because they kind of resemble little like sort of rock pool currents, where they're teeny tiny. They're not like sort of going all the way around the iron core. But because of the changing magnetic field, and the changing magnetic field is like forcing the electrons of the iron core to move in the same way that they force. So a changing magnetic field in this conductor is forcing the electrons around this secondary coil. Well, this is a conductor with a changing magnetic field through it, so it's not exempt. Exactly the same thing's going to happen. That's going to do work to drive the electrons of the iron core around. And that's what eddy currents are, and they're bad because driving those electrons around against resistance, it takes energy to do the work to push those electrons around. So ideally what you want is, yes, this primary coil is creating the alternating magnetic field, that is driving the electrons in the secondary current round, but we want it to use all of its energy pushing those electrons round. We want it to spend all of its energy driving the secondary voltage and not much of its energy flipping around the magnetic field in the iron core or pushing around the iron core's electrons. We want the iron core to help, not get in the way, which is why we talk about these hysteresis loops and these eddy currents. Because it's not like, the iron core and the secondary are both conductors, and so the same thing happens in both. So hopefully that makes a bit more sense there. Right. Do I need to clarify? Let me see quickly, just to make sure this is good for IB as well. I have not taught explicitly. I haven't seen the this idea of, where was this? Yes, self-induction and mutual induction. So I'm seeing something here. So self-induction is induction within the same circuit. So it's an effect in which a change in the current. Hold on, let me stop sharing screen here for a second. So it is the effect in which a change in the current tends to produce an induced EMF which opposes the change in the current in the same circuit, which is so wordy. um, so basically what's happening here. Okay, so let's say, okay, got it. Right, so this is kind of the final thing I want to talk about. If we've got a wire with a current, if the current changes, what's going to happen is the magnetic field, we know from the left-hand rule, from all that kind of stuff, the reason why it happens is because when current is moving in a coil, that creates a magnetic field. If that current changes, the magnetic field changes. Well, would you look at that? We now have a changing magnetic field around a conductor. Is that right? No, I'm not liking this explanation. Yeah, no, I don't enjoy that explanation. Not well explained. I wonder if I can think this through. Because this is honestly like the hardest part of the A-level syllabus, I find, to really wrap your head around, is this idea of back EMF. So let's see what this textbook says. Yeah, no, I'm not enjoying that either. Okay, so maybe I'll go away and see if I have a think about that. Whoop, overshooting the mark here. But in terms of like the core stuff to do with electromagnetic induction, I think this is a good sort of introduction and primer for how to do that. Someone says, do you know how to derive fundamental formula from scratch with integration? Yes. I may as well touch on that because we're here and I'm interested. And this is something that maybe would be sort of taught to you a bit better at university. But let's talk, for instance, I think I know you. I think you're not doing further math. And if you could confirm that you're not doing further math, that would help. If you are doing further math, you've kind of been introduced to this concept already through the idea of volumes of revolution. So for instance, let's do the area of a sphere using volumes of revolution. Is that the best way to? Yeah, we can try it. So let me show you how that works. Yeah, you don't take it. I thought I recognized you for that. Okay. So let me show you what your peers understand. So let's say we have a general function, right? Which does something like this. And let's say we wanted to take this and we wanted to rotate the entire thing around the x-axis. This is the best art I've ever done. I'm giving myself credit for that. So let's say we kind of rotate it around, right? Full 360 to create this kind of vase shape. If you wanted to get the volume of this thing, so this is y, this is x. This is constantly changing, so it's a little bit weird to consider. But if you remember how to do differentiation from first principles, we assumed that on a curve, if the 2 points are close enough together, it is approximately linear. And we can use that exact same idea here. So let's take a little slice of this. So we can see on the whole it's curved, but here these look a lot much more like straight lines, right? And what's more, if the variation is tiny, then these are basically exactly the same y value. So what we say is for a little strip of width delta x, it's approximately a disk. It's approximately a disk which has an area, so this has a y value. So this is kind of a circle going into the plane of the paper, and the circle has area pi times y squared. So the radius at that point is y, going all the way through and round. And the thickness of that is delta x. And integration from first principles, what we say is the volume is the sum of these disks. So it's the sum of the pi y squared dx's. Now, the integral, now the limit basically as delta x tends to 0, the limit of this guy is the integral of pi y squared dx. And so this gives us a formula to find the volume of revolution. So the idea is if you can create these small elements, as we call them, and then think about the limit as the delta x tends to 0, that creates an integral from first principles. So another way we can do this is volume of a sphere. Let's consider a different kind of elements. So we use the word elements a lot. So let's say we want the volume of a sphere of radius r. Well, let's consider a small element. So with this one, we're going to call them shells. So let's consider a small shell of thickness delta r. That's too small. Oh, if you thought that was genius, you're going to love this. So so you basically just sort of geometrically kind of come up with the volume of this thing and then add up all of the different shells. So this is kind of similar to like, how if you add like layers, you know, the people who put on like 60 t-shirts, every t-shirt you put on, you get a little bit thicker. So it's almost like finding the individual layers and then adding them up, almost like 3D printing. So here, this thickness would be a delta R in there. And it's so thin that we can consider the volume of this thing to just be the surface area times that little thickness. It doesn't really matter that the outside surface would, strictly speaking, have a bigger surface area than the inside surface. Because delta R is so small, they're basically the same. So we're going to say the small volume element is the surface area of that inner sphere, which is 4 pi r squared, times the thickness. And so the volume is the sum of all these little volume elements, which is the sum of all the 4 pi r squareds delta r's. And then the integral is the limit as the delta r tends to 0. So the volume is the integral of 4 pi r squared dr, which is 4 pi r cubed over 3. Just by doing that integral. So that's all integration from first principles is. You kind of think about what you want to integrate. And this, by the way, even works less with volumes. This even works with areas. So like if you think about finding the area under a curve, which you're super used to from the normal A-level syllabus, right? So let's say where we were finding, let's say we had y equals x squared, and we want to find the area under x equals 2, right? So y equals x squared. We know that you would just integrate it between the limits of 0 and 2. Why is that? Well, the area is going to be the sum of all the little area elements. And an area element is just going to be, well, if delta x is small enough, we can approximate these as being rectangles. And the rectangle is going to have a width of delta x and a height of y. And the limit as delta x tends to 0 would be the integral of y dx. And that is exactly what you do. You integrate y with respect to x between the limits of 0 and 2. So that is integration from first principles. Thinking about the shapes that you want to add up to make up the whole, and then considering the limit as delta x or delta r or whatever you're talking about tends to 0. So you were saying, initially I was thinking more like how we find the center of mass, where you find the mass of a strip and then calculate it for the whole body. That just is the surface area of a sphere. We can take that as given, right? Okay, no, fine. Make me do it another way then. No, I can do it another way. Aha. Let's do it using this volume of revolution idea. So if we did the volumes of revolution, let's model a half circle where we know this would have been x squared plus y squared equals r squared. So we can say that y squared, if we consider this to be y and this to be x, so y squared would be r squared minus x squared, and y would be equal to r squared minus x squared to the half. This would be r, this would be minus r. We could consider taking the volume of revolution of that. Yeah, zipping past stuff is not fun. So let's find the volume of revolution of this thing as we rotate this thing through, right? So if we rotate this thing, so if we rotate this thing through, we know we're going to get a sphere. And we know the thickness of these elements is going to be dr, or dx, sorry. It's going to be change in x. And again, we know that the volume, the volume of this disk is going to be, well, the radius at that point is y. So the volume element is pi y squared delta x. So in order to find the volume, we're going to have to find the integral from minus r to r of pi y squared dx. But y squared is r squared minus x squared. So this would be the integral from minus r to r of pi r squared minus pi x squared dx. And now we just run the integral. So that was the theory. Now we can just go, oh, wait, I know this skill. This skill is going to be fine now. So we've got pi r cubed over 3 minus, no, lies. No. Because we're integrating with respect to x. So this would become, this is just a constant. So it would be pi r squared x minus pi x cubed over 3 between r and minus r. So running that through, we would get pi r cubed minus pi r cubed over 3. And we subtract from that minus pi r cubed plus pi r cubed over 3, not making any sign errors. So this would be 2 pi r cubed over 3 minus 2 pi r cubed over 3, which would equal 4/3 pi r cubed. Ding, 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 we have a winner. Now, you asked me, how do we know that 4 pi r squared is the surface area of a thing? If you differentiate it, you will get that. Now, we can do even better though, right? Let's go back. Let's consider the surface area, right? How would we consider the surface area? Well, to consider the surface area, let's, instead of getting the volume of this thing, consider like a shell that would be made by rotating the arc length through, right? So what we would do here, that would be a little more complicated. Let me draw that out. Let's see if I can derive that. So let's consider one last time a circle, but this time it's with this. How would I do that? Would that work? Because this feels more like I want to do it polar at r theta. But then we would need to do, and that would be complicated. Okay, I don't think off the top of my head, I would be able to do this using this coordinate system. And then I think that would get complicated introducing new coordinate systems. Of course I can do it. Come on now. What am I talking about? What am I talking about? Right, so the volume element of this thing. Well, okay, let's instead consider the area element of this thing. So the area element of this thing, well, that would just be like a hula hoop shape. That would just be the circumference times dx. And the circumference is 2 pi r. What have you stumbled across? Sorry, we're doing integration for first principles now because we pivoted. Hi, sorry about that. It got fun. It got fun. So so what we would do here, that would be the area element of this disk, right? It would be the circumference of the disk, which would be 2 pi y times the thickness, delta x. And so the area, the surface area of the full thing would be the integral from minus r to r of 2 pi y dx. No, this would get complicated now. That would get complicated. Yeah, you would have to do it in a different coordinate system, I think. Maybe. Do I want to integrate that? I really, really do not want to integrate that. All right. Well, I'm going to leave it there because I think that at least like demonstrates the principle of integration from first principles, where you just sort of come up with your little disk or your little element, work out the quantity on the element, and then sum that up over all the elements, and that constructs your integral for you. So that's good fun. Totally irrelevant to electromagnetic induction, but I don't care. So that's fine. So hopefully that sort of you find interesting. I could do it. Hold on here. Okay, I'll show you wherein the problem is, because the first one was easy to integrate. This one's not easy to integrate because this would be the integral from minus r to r of 2 pi root of r squared minus x squared, which is not as easy an integral to do. I think it might. Do I have the A? Because I think you would need some A level. Let me see if it's there. So because I don't have my standard integrals memorized. A level maths formula booklet. If I find and I scroll through for the A level, you will find some standard integrals. And if I look hard enough, I might be able to find the standard integral in the correct form. I've now got to the part I'm looking for. No. No. Am I doing something stupid? Because that doesn't integrate well, I don't think. Is there a regular streaming schedule that I have? Okay, so first of all, I've got a Discord server now. Ha ha ha. So that is where I will send any sort of streaming updates. On the whole, I think that what I'm doing is largely, obviously this is a little weird because it's in half term. In regular term time, I'm usually going live Monday mornings for a math paper live solve. And typically it's been Wednesdays at 5:30 for this kind of evening theoretical discussion, more interactive stream. So Wednesdays at 5:30, if you want to bookmark that, is, especially as my schedule fills up, pretty much the only slot I've regularly got. So you can kind of bank on that as being when I would do that. You just joined, so be people in the Discord server now. Theoretically speaking, general. People have joined. This is interesting. I still have to work out how to like do, because I'm not of Discord, so I have to kind of work out exactly how to make this happen. But if you guys have any recommendations, in streaming updates, that's where I should put my streaming schedule. So I'll let you know sort of in advance when I'm going to go live. Typically, that's going to be Wednesdays at 5:30 and Mondays at 11 a.m. with very little variation. So I'll keep you guys updated on that. But in the meantime, let's call it there. So yeah, feel free to keep coming. I'm happy to. So I have a kind of loose idea of what I want to cover in each of these sort of like weekday evening live streams. But if you have particular like topics you want to go over in physics or in math, if you want me to do a bit of a deep dive, feel free to pop those in the Discord server in the streaming suggestions channel. Because then I'll kind of like, at least then I know I'll be doing something that's interesting and engaging for the people who are actually here. So yeah, feel free to drop those in and I'll kind of keep making those happen. And in the meantime, feel free, well, update though, I should put this in the server. Next week, I will not be doing an evening live stream only because I'm going on holiday because I can feel the burnout in my bones. So I'm making sure to get a good rest in before the blitz of exam season begins. Got to make sure my energy levels are right because otherwise I am not going to make it. So next Wednesday, I won't be doing one. Ooh, and thermal physics, great suggestion. People do not get thermal physics. Okay. So yeah, next week, no evening one. I will still be doing the math live solve on Monday, probably 11 a.m. Now, because it's a live solve as well, like you don't need to be there in the chat as much. So I don't mind doing that while you guys are in school. You can kind of catch up on that because all my streams go to YouTube, like sort of you can watch them sort of on catch up. So the live solves is much more me ignoring chat, whereas in the evening when you guys are here, it's much more interactive. So Monday, the live solve is going to happen. Wednesday, the stream is not going to happen. And then from March, it should hopefully be nice and regular. So in the meantime, you guys enjoy your week off from me. I will see you guys in the evening on probably Wednesday, March the 4th. In the meantime, keep working hard, manage your energy levels well, enjoy the rest of your half term, because this half term is your last learning opportunity because you feel it in April. Once Easter hits, then it's exam season proper. So just make the most of this half term. Give yourself like the least, like if you do some good preparation now, you'll feel like you have less revision to do at the end. So just make it happen. You guys will do fine. So I'll see you guys maybe on Monday morning. And if not, then I'll see you on Wednesday the 4th. So take care. I'll see you guys then. All right. Bye-bye now.